I'd like to thank all judges, sponsors, the VJAS and VAS committees, and of course you all, the students, for all of your work. All of this hard work, practice, and research has finally paid off, and you have survived your presentations. Give yourselves a round of applause, please. Congratulations. I hope you all have enjoyed yourself today. By the way, I am Yashodhara Varma, the co-president of the VJAS student body.
I am Reona Pereira, the other co-president. So I hope you all have been taking lots of pictures and posting about your experience. If you haven't done so already, please use hashtag VJAS 2017. Whip out those phones, grab some friends or someone random and post a selfie. Caption it with something clever or interesting, because remember, one lucky person could win a Target or Kroger gift card for a thoughtful or funny post. I would also like to re-acknowledge our current student officers who have been doing a lot of behind-the-scenes work lately. You might have seen some of them walking around and filming and interviewing and such, so please give a round of applause to Ankit Kumar, the secretary, Cory, Dudka, regional director, Sarah Jackson, STEM chair, and Cassia, blog editor-in-chief / communications liaison. Thank you.
Now, I would like everyone to put your hands together and join me in welcoming the Virginia Academy of Science President-elect, Dr. Robert Atkinson.
Good evening, and please, can you hear me in the back? No. How about if I use this? Is this better? The ability to learn, yes, it's a lovely thing. So I would like to have my first official act to be introducing the person who has brought us to this campus for the Academy, and that is Darcy Mays. Darcy, would you come give a welcome to everyone?
Thank you, Rob. He said give a welcome, but I think instead, since you've been here for a day, I think the proper word is a thank you for coming and joining us here at VCU. We know that you are the future of science and math and engineering and health. And we here at VCU, and I'm sure this is true of all of the institutions that VJAS travels to, we really appreciate you coming to our campus. So on behalf of our president, Dr. Rao, our provost, Dr. Hackett, the two of them have generously supported the activities of this conference, and then the deans of our science schools, Dean Fuentes from Humanities and Sciences, Dean Boyan from the School of Engineering, Dean Buckley from the School of Medicine, and our Vice Provost for Life Sciences, Dr. Tomes. I would like to, again, welcome you to VCU, but again, thank you for your attendance, and I hope you enjoy tonight's talk, you enjoy the other fun activities that will come up later, and you have a great time at the award ceremony tomorrow morning. Thank you.
And I'll just say a couple more things, because I'm really the warm-up act for an excellent talk you all are anticipating about the Anthropocene. So that's our headlining talk tonight. I did want to just say something as the incoming new president of the Senior Academy. First, don't get used to seeing me in these clothes. I'm a swamp researcher, and my students at Christopher Newport University and I spend a lot of time tromping around in the mud and forests of the Great Dismal Swamp. Has anybody ever heard of an Atlantic white cedar? Some have heard of it. Very good. Have you heard perhaps the recent news that the last stands of it in the Dismal Swamp blew down in a hurricane, were cut up in salvage logging, set fire to, and then 3 years later burned again? So I'd like to act that out for you. That's what happened to the Atlantic white cedar swamps of the Great Dismal Swamp. So, thank you. So, you might be asking, what does that have to do with you? Because hopefully you've had a better last few years. You know what? You've done something really impressive, and you know that, and we keep telling you that you have completed a research project, which many of your peers did, most of them did not. Then you went to the great trouble of preparing it, submitting it, and getting accepted to, and then presenting at the Virginia Junior Academy of Science. And I just don't know whether or not you know what path you are on. As in the Senior Academy, or we just call ourselves the Academy of Science, we view you all in a capacity I don't think you realize we do. That is, we view you as prospective colleagues. Okay, what does that mean? Well, so the Virginia Junior Academy of Science has helped you become the scientist that you've become. And in probably anywhere from a few months to just a couple of years, maybe 6 years at the most, you'll be going to a college or university, perhaps in Virginia. And when you get there, the faculty are likely to be members of the Virginia Academy of Science. And the very first thing they'll tell you when you show up at their office and say, hey, look, I've been doing research. I like that. I get it. May I help you with your research? What they'll say is, sure, let's ask for some money, and who are you going to ask? The Virginia Academy of Science. Right. Now, the faculty member may already have their own money, the research may not take a lot of money, so anyway, maybe you get the research done. Where do you think you go with your findings to present them at a conference? The Virginia Academy of Science. Yeah, I think you're getting it. Okay. And if I asked for you to raise your hand, you'd probably say, yes, I agree, that's probably it. But it is not. You might present year after year as a college student at the Virginia Academy of Science. And then as an undergrad possibly, but certainly when you go on for a master's or a PhD, you'll do research that could end up in an actual publication. Right? That's the kind of thing you've been told to cite in the papers you presented. This way you would be an author of that. And guess who has the Virginia Journal of Science where you could publish your findings? It's the Virginia Academy of Science. So do you understand why I say we're colleagues? Because I want to publish in the Virginia Academy of Sciences Journal, the Virginia Journal of Science. And nowadays, the research would be discoverable on the internet, free to anybody who wants to find out what you've learned about maybe Atlantic white cedar in the Great Dismal Swamp, or whatever it is. I know I heard a bit about dust mites and allergies to dust mites. So there's tons of research things, all of which you can participate in and through with the Virginia Academy of Science. So on behalf of the Academy, let me welcome you to what we hope will be a career journey you'll take with us, and congratulate you on everything you've done so far. I think it's time to give yourselves another round of applause.
This evening's George W. Jeffers Memorial Lecture will be given by Jeremy S. Hoffman. Dr. Hoffman, Climate and Earth Science Specialist at the Science Museum of Virginia, is a paleoclimatologist who likes to engage diverse audiences with climate science and concepts and data. He earned his doctoral degree in geology with a focus in paleoclimatology as a National Science Foundation Graduate Research Fellow in the College of Earth, Ocean, and Atmospheric Sciences at Oregon State University. Dr. Hoffman has also served as a Science Communication Fellow for the Oregon Museum of Science and Industry and the Mitchell Hamline School or College of Law.
He earned his BA summa cum laude in geology with distinction at Augustana College in Rock Island, Illinois. Dr. Hoffman's research expands our understanding of Earth's climate from ocean archives to help us understand how the ocean interacts with other parts of the climate system. Specifically, his work has increased our understanding of the climate during the last interglacial period, about 130,000 years ago, the last time Earth's climate was generally comparable to ours. Please give a round of applause for Dr. Hoffman.
Let me just set up my turntable here really fast. Hey, there it is. All right. Hello, everyone. I was told by my new friend Isaac from Arlington that I'm like the Taylor Swift of this evening, and that I guess I'm the headliner. Not something I'm used to, but I'm Dr. Jeremy Hoffman. I'm the Climate and Earth Science Specialist at the Science Museum of Virginia, just down the road here in Richmond, and I study climate change. And I know that might seem like a dirty word these days, but what I want to really talk to you about tonight is something called the Anthropocene, and specifically growing up in this time period. But in order to do that, we have to go real far back, not just Throwback Thursday. I'm talking like billions of years. So this, if you're not familiar with it, is the entire history of the world, locked up in rocks, basically. So what we're looking at is a section through Earth's history. The top, where that wonderful pickup truck is the present, and down at the bottom is the very formation of the Earth about 4.6 billion years ago. Now, there was a video that came out just the other day on YouTube that you might have heard of. It's called The History of the Entire World, I guess. So the thing is it's actually remarkably accurate. So the Earth itself was formed from the remains of old stars that blew up. So the Earth itself was formed from really crazy stardust. And then the things that live here on that planet are also made of that stardust. So inevitably we all come back to the point that we originated as even crazier star stuff that gravity pulled together and turned into the Earth, and then we all kind of go from there. So that's kind of the initial start of it. But then I want to talk about a couple billions of years later, what's a couple billion years here and there, is my favorite dinosaur called Cryolophosaurus. And but I guess just to back up really fast, when a new time period in geology starts, it has to be some globally synchronous thing that we can go and point to and say, oh, this is where that part ends and this part begins. And before the dinosaurs, that was the Great Permian Extinction, when a lot of our oceanic and land dwelling, which weren't very many, but a lot of things died off at the end of the Permian. Now, then in the Mesozoic, which I'm going to go here, is when the dinosaurs evolved, right? And my favorite, called Cryolophosaurus. Who here has heard of Cryolophosaurus? 1, 2, 3, all right. So, when I was in college, one of my geology professors would go down to Antarctica. And I asked him to be a part of some of the work that he was doing, just like Dr. Atkinson told you to do. And I got to work on some bones from Antarctica, from the Transantarctic Mountains, which run through the middle part of Antarctica, separating East and West Antarctica. You might have heard of West Antarctica because it's the thing that's really contributing a lot to global sea level rise right now because of global warming. And then East Antarctica, which is the largest bank, the largest natural bank of fresh water on the planet. There's about like 300 feet of global sea level equivalent water in the East Antarctic ice sheet. But running through the middle is this artery of mountains called the Transantarctic Mountains. And in that was a rock where there was a dinosaur waiting to be discovered. Now it was called Cryolophosaurus, but if you look really closely, it's sporting a comb-over, much like me, and which is, when it was discovered in 1991, was referred to as the eldest dinosaur. Now what's important about that, and this is going to come up again later in the presentation, is that sometimes when a scientist says something, he or she or they can never live it down for a really long time. And my old professor in geology said that he wishes he would have never referred to it as an Elvis poof or a pompadour, because for the rest of his career people have said, oh, you discovered the Elvis dinosaur. And surprisingly, no relation to Elvis. But anyway, that's my favorite dinosaur, called Cryolophosaurus. You learn something every day. Then a couple tens of millions of years later, there was another thing that happened that geologists can point to and say, hey, we could go all over the world and find rocks that have dinosaurs in them. But then there's this weird thing that happens where all the dinosaurs just stop being in the rocks. And it all seems to be happening about the same time. That so happens to be about 66 million years ago at the Cretaceous-Paleocene boundary. And again, I will turn to the history of the entire world. Oh wait, first, I have to describe how that came about. So scientists were looking at this layer of rock right above where they couldn't find dinosaurs anymore, and where they did find dinosaurs. And in that little layer of rock, this little clay layer, which this person is holding here, is an isotope, a flavor of an element that is only created in the explosions of atomic bombs. Here now, at least in the present. So that's pretty amazing. It's like, wait, well that's like just after the dinosaurs. What's going on here? Well, it turns out that that you can go and actually see this in Italy. This is me a few years ago with a couple of my friends, Reona and Gloria, and we can actually point at that layer. And that's where basically where the understanding of how the dinosaurs ended up disappearing came from, which was, as you might be familiar, was a big asteroid, a big meteor that crashed into the Earth in the Gulf of Mexico. And the dinosaurs were gone after that. But it was started with a hypothesis, right? So it was like we made an observation, no more dinosaurs, there are dinosaurs there aren't dinosaurs, and it's because of this amazing thing that now mammals got to evolve. And that's where we kind of come up to where Homo sapiens, people, might surprise you to find out that Homo sapiens wasn't the only common ancestor to people that were around on the Earth at the same time. Actually, there's like a raging debate right now in the scientific community as to what happened to the other Earth-like, human-like organisms that were like us. Did we assimilate? Did Homo sapiens learn how to get into their communities and then they interbred and then they just disappeared? Which is not supported by genetic evidence. So what does that leave? That actually kind of leaves a bad thing. That means that we pushed everybody away and we decided that they weren't allowed to live the same places that we wanted to anymore. So anyway, that happened about 200,000 years ago, and slowly all the rest of our human-like ancestors disappeared. And so now we, have cars and all those things, but what you don't see on this list is the Anthropocene, the thing that I teased you with in the title of my talk. Now, the good question to ask after looking at this in the brief history of the world that we've just gone through is, what the heck is the Anthropocene? And to do that, we have to meet this guy, Paul Crutzen. He's an atmospheric scientist who's famous for discovering that humans could actually alter the chemistry of the atmosphere. So it was like, for a long time, people were like, yeah, right, we can't touch that far high up into the sky. Look how far away it is. But he was one of the first people to show that stratospheric ozone could be destroyed by human activities on the surface. So he won a Nobel Prize, and along with that Nobel Prize, he was also awarded the worst Coachella outfit ever, which is that headdress. I asked some colleagues whether it's okay to make fun of a Nobel laureate. They said it's okay. But also you might notice that this is an old white dude. And I'm going to follow it up that you're going to hear about a lot of old white dudes in the subsequent slides. And that's, that's something about science that we're working towards making better. It's great to see such a diverse crowd of scientists in this room. You're doing great. And hopefully someday we won't have as many old white dudes to talk about. But anyway, so what is the Anthropocene? We can define it in a bunch of different ways, okay? And the thing is right now, the scientific community is like, what are we going to do to say whether or not the Anthropocene is something? What we can do is we can point at a bunch of different things that have been going on. And this graph, I know some of you probably can't see it because of this podium, or for another reason, angles or whatnot, but all these graphs go from about 1750 to the year 2000. And what they're all showing is an exponential increase in what they are reporting. So across the top, there are gases in the atmosphere like carbon dioxide and methane over in the corner. And then there are things like the amount of tropical wetlands and stuff that we've lost, and the number of species in the thousands, global biodiversity that is disappearing very rapidly. So these are all things that are happening about the same time, rightly starting about 1900, 1950. But then there's, these are kind of things like the northern hemisphere average surface temperature. That doesn't really mean much to me very much in my lifetime, but things like this do. So we can talk about urban population. We went over 7 billion people in 2011. There's also things like the amount of telephones down here in the bottom middle, the number of telephones in the world. That is an incredible growth in the number of telephones. But my favorite data set on this slide is the number of McDonald's restaurants. Because I really think that it is the spread of fast food and the industrial agriculture that comes along with it that really shows that that people, Homo sapiens, have exerted such a concentrated control of the planet. And that's really what the Anthropocene means. It means that humans have made themselves the #1 geologic force, the natural force that's driving the planetary trajectory. It's all up to us now. That's what the Anthropocene means. But there's some other things that we can point to, such as plastic conglomerate. So this is in Hawaii. This was discovered a couple years ago, and it is lava that melted plastic to make a new rock. Now, like I said, the geologists look for that thing around the world that they can point to and say, oh, that's the Triassic. Well, you couldn't go everywhere around the world and say, plastic conglomerate, the amalgamation of lava and plastic, which is gross. You can't go around the world and point to that. So we have to look elsewhere, but that's one interesting candidate. Another one might be just the amount of trash that we've left behind. You're looking at a photo that was taken by a submersible from the National Oceanic and Atmospheric Administration in the Marianas Trench, about 3 miles deep in the ocean. And there is a pristine can of Spam. And I was going to put the empty Budweiser can, but since you all are of age, it's not funny. But the Spam can, I think, does a pretty good job of explaining that even though we might think that the deepest part of the ocean is really far away, it's not. And in fact, we could go even deeper. 3 miles isn't as deep as the rest of the ocean. The deepest part is about 10,000 meters deep, okay? And the little tiny crustaceans, or they're called amphipods, they're basically like really weird alien shrimp that live at the bottom of the ocean. And some scientists went out and collected a bunch of them. And when they measured what was inside their stomach, it was flame retardants. The things that we've made up to use in our industry have made it to the very deepest part of the ocean and have polluted even the most unreachable, in our minds, the most unreachable organisms. So one thing I'll have you think about with me is that the deepest part of the ocean is about 6 miles deep, okay? About 10,000 meters. But the island of Manhattan is 12 miles long. So even if you were to take the island of Manhattan and put it on from tip to nose, you would only make it to about Midtown, and that's the bottom of the ocean. You know what I mean? It's not that far away. It's just something that we need to start realizing, that these systems that we've thought to be so disparate and disconnected from our everyday lives, actually, here's proof that they're not. So, what's another thing? More along the lines of trash. This just came out the other day. It's a study published in the Proceedings of the National Academy of Sciences, which is kind of like the big brother to the Virginia Academy of Sciences. But an island that has been uninhabited for 600 years had 37.7 million pieces of plastic trash on it. And what's funny is that I was watching the news, and this actually hit major national news. And they said, boy, I'm so glad that nobody lives there. And I was like, wait a minute, I think that we're not thinking about that the right way. We should be thinking about it as, I wish I could be in Castaway and not have to deal with a dirty, plastic bag washing up on shore. I want to have that pristine ocean island somewhere that we've never touched, but we have. Even the most remote island, there are hula hoops and coolers and stuff all over it. So probably my favorite thing to point to, because I'm a paleoclimatologist, meaning that I study how the Earth has left behind clues for us to figure out about itself. It's like being a mystery solver and trying to figure out what's gone on in the past so we can better understand the future. And what you're looking at here, this red line, is the concentration of atmospheric CO2, the potent heat-trapping gas that you've heard a lot about, over the last 800,000 years. You might be asking yourself, rightly so, hey, how do we know that the CO2 level 800,000 years ago? You'd be right, it's kind of far-fetched, but what's really great is we can go to places like Antarctica where snow accumulates every single year. I have friends that do this from Oregon State University. If you would like to hear more about the paleoclimate program at the Oregon State University, I'm happy to tell you more. But you can go to Antarctica, watch the snow accumulate, and over time it builds up, and as it freezes, it traps little tiny bubbles in it. And we know we can follow that down until it disappears, until it goes into the middle of the continent. And we're like, what? So then what we did is we took a big drill and we drilled down to the very bottom. We counted the layers, and there it is, 800,000 years of CO2 record. We can measure the gas that's trapped in those bubbles. And what we can see here is that the atmospheric CO2 level basically varied between about 175 parts per million at the low end, at the bottom, to about 275 parts per million at the high end, for about 800,000 years. Then something happens at zero, at us, at the Anthropocene. Where we are at that red dot is about 410 parts per million. Other paleoclimatologists have shown that CO2 is now higher than it's been for many millions of years, and by the end of the century, if we don't cut back, we will approach CO2 levels in the atmosphere that haven't been seen for 400 million years. 400 million years. So, that's pretty serious, I know. This is a funny thing. My friend Benjamin Cook from NASA GISS thinks instead that the Anthropocene is going to be Keurig cups and mean internet comments, which I think isn't far off either, given everybody knows not to go searching in the internet comments. But a good question now to ask is, who the heck is this guy? Who am I? And why do I, I wish you could all see it better. Yeah, it's a fry meme. I put a fry meme into this talk. So for those who can't read it, it says, not sure if this guy is cool or he just talks really loud. And I can assure you it's a little bit of both. But I want to take you through kind of go through a journey with me, okay? And we're going to go through the Earth's temperature since 1880. On the bottom is time. That's never going to change. It's going to go from 1880 to the future in 2020. And then on the y-axis is the Earth's temperature change. So you might wonder why we're looking at temperature change. Well, if you leave your house, you want to know how far away from home you go, right? And that's kind of the same principle of an anomaly, or the change relative to a baseline. I want to know how far away from home, or about 1900, the Earth's temperature has gone. Then we're going to cover some major milestones in climate science, and major milestones in my life. I'm going to share some baby photos with you. So let's get started back in 1896. So Svante Arrhenius, another old white guy, discovered in 1896 using math that was worked out by Joseph Fourier in 1824, and then measurements made by John Tyndall, another old white guy, in 1859, that said that if you increase the amount of heat-trapping gases in the atmosphere, the Earth's going to get warmer. And Svante Arrhenius, he calculated out that it would be about 5 degrees Celsius if we doubled CO2. So that would be about 560 parts per million. We're at about 410. Given all the time that's passed, over 100 years, we've kind of deduced that the number is actually probably closer to 3 degrees Celsius. But the uncertainty on that number envelops Svante's old estimate. So even something, you're the first person to say something, everybody else has to spend the rest of their careers trying to prove you wrong. And unfortunately, we haven't been able to say without a shadow of a doubt that Svante Arrhenius in 1896 was wrong about climate change. So just remember, climate change is not something that was made up before you were born. Well, it was before all of us were born, 1896. Then in 1938, we're going to go through a little bit of time there, and another old white guy, Guy Callender, is the first one to link together the association of increasing CO2 and the increasing temperatures at the Earth's surface. He actually had to go around the world and say, hey, can you measure CO2 for a while? And can I have all of your meteorological data? I don't know how many people had to track down data for their projects, and it's really tiring. Yeah, and some people don't tell you like how they report things, and that was like the story of my PhD. But in any event, he was the first one to say, hey, there's a CO2 effect to the Earth's increasing temperatures. And everybody was saying, Guy, no! People can't affect the world. Come on, it's too big. We can't see all of it. But it's played out exactly as Guy Callender predicted. Now, in 1958, there was a video released. You should go to YouTube and put this on your playlist. It's a video called The Unchained Goddess by the Bell Labs people, and it's an hour-long documentary about how humans are unwittingly changing the climate. So already in 1958, we were pretty woke to the idea that humans are changing the climate through the byproducts of their civilization. But it doesn't stop there, because in about 10 years after that, Cesare Emiliani was the one to say, using the techniques that I used in my PhD, this guy made them up. So he went out into the Caribbean Ocean, he took a hole punch at the bottom of the ocean. Why would you do that? Well, organisms that build their houses out of the water that they're living in, they die and sink to the bottom of the ocean. And then they accumulate laterally, just like you saw before. The oldest stuff is at the bottom, the youngest stuff is at the top. And Cesare Emiliani used some World War II magic, also known as isotope geochemistry, to determine that the Earth goes through regular patterns of ice age and not ice age. And what he said in this paper in 1966, something that he would never live down, by the way, oh, he's coming full circle, he said that the Earth would be going into an ice age in 1966. He said sometime in the next thousands of years, we'll go to an ice age. And according to Milankovitch theory, that is true. The way that our orbit is arranged around the sun changes on very predictable timescales. And right now, we should be, on average, thousands of years going towards an ice age. But a lot of follow-up, we know that that's not longer going to happen. Anyway, 1981. Now we're in the 80s. Woo! My decade. Well, in 1981, James Hansen, another old white guy, predicted the first time using global climate models what the next century of global temperature was going to do. Okay, based on what had already gone on, the amount of CO2 we put in the atmosphere, and that's what it looked like. It was like, hey, what if we stop burning fossil fuels? What if we don't? What if, and this is kind of what they came up with. But now we can use our actual observations to show that it's actually been much worse. So already back in the 1980s, when we were making our first conservative estimates of what the planet's temperature was going to do, it's actually played out worse. So that's good. 1988, the best year, really. 1988 is when I was born in Chicago, and Chicago, Illinois. And it was the 3 warmest years on record for the first time. The first time that we were like, hey, it's the 3 warmest years on record. Don't worry, we're going to come back to that. But also the Intergovernmental Panel on Climate Change was formed, which is the group that was put together by a bunch of governments to tell us what we know about climate change. And right away the scientists say, hey, by 2005, we should stop doing the thing that we do, where we burn fossil fuels and put CO2 in the atmosphere. And then everybody was like, no, scientists, we can't do that. The Earth's too big, come on. Then that's what I looked like 2 days old. And what's really funny is like my dad, that photo of my dad, like you look at similar kinds of angle photos now and it's like spot on. So it's just funny. I don't have any kids yet, but that's kind of what I looked like. Then in 1991, I'm 3 because math works. And Shell Oil actually released a video called the Climate of Concern. Yet another video that I suggest that you peruse on your free time is called The Climate of Concern. And basically used our understanding of climate change then to predict what climate was going to be doing in the next couple decades. And what's really important about this is that Shell Oil had this video and they released it for their own employees and the public never really knew about it. But so they should have been worried about me because my brother and I were Batman and Robin and little did they know that we were going to try and save the world. But this is kind of what they show in that video. So what we're looking at, I hope everyone can kind of see, is that this is an actual scene from that documentary. And what they're showing is the Earth's temperature until about 1988 or 1991, and then the projections. And actually that has all pretty much come true. The same stuff that we were talking about in the 90s, when I was 3 years old dressed up as Robin, has come to pass. So that's an amazing thing about science, is when you know a lot about the subject that you talk about, it turns out that it works. Now, 1995, this is really amazing, because this is when stuff gets to get real good. We come up with this thing called fingerprinting. And basically we can start to isolate individual variables in the climate system. So like, hey, I only want to know about volcanoes. Hey, I only want to know about CO2. Hey, I only want to know about clouds. We can do that now because computers started to be awesome. Anybody remember Windows 95? Your teachers do. Yeah, so yeah. So anyway, that's Ben Sanner et al. And then that's what I was doing when that paper came out, swimming without, I actually remember getting really severely sunburned, and you can see my personality starts to come out about this age. I'm kind of making a weird face. But anyway, this is what detection and attribution is. So detection is basically what you might think. We want to find the signal outside of natural variability. So the Earth kind of goes up and down, has its cycles. You hear about these cycles. Well, then there's stuff that kind of rises out of that, like an El Nino or the North Atlantic Oscillation. Those things happen and go like this. But then when the Earth started just going like that, that was detection. Now attribution is the magnifying glass there. That's what I was saying before, where you can actually say, hey, I want to only hear about volcanoes. Or I only want to hear about the sun's energy that fluctuates on about 11-year timescales. And what's really amazing about this paper in 1995, it was the first one to say, hey, if you only do CO2, the Earth warms up, and if you put sulfate in there too, what we burn what we generate when we burn coal, when you put those things together, the Earth looks a lot like how it looks now. And everybody was like, oh, that's interesting. Maybe we are doing the thing that we were before, everybody said, since the 80s. But still nothing happened. In 1998, there was the monster El Nino that made Earth's temperature shoot up, much like it did in 2016. But I am 10 years old and celebrating. Yes, it is real. It is real. I'll give you a second to let that sink in. Yes. During the warmest year on record, I had that haircut, which I'm happy to tell you how to do, by the way. If it's super flame, I can hook you up, fam, no big deal. But basically, 1998 was the warmest year. I'll give you a second, I know it's embarrassing. Turns out when you're an adult, you're not that ashamed of it anymore. It feels good. Oh, not that good. Okay, but 1998 was the warmest year ever recorded, in the warmest decade ever recorded, and using tree rings. So, okay, there are things, how many people here cook with coconut oil? I mean, yeah, coconut oil, step your game up if you don't, it's amazing. But the thing is coconut oil, if you've ever had it in your kitchen, it is solid at room temperature, generally. But then if it goes up just a few degrees on a hot summer day, it'll melt. That is a very sensitive fat to temperatures. You can see that change. There are things out there in cells of organisms that are living in the ocean that work the exact same way. And we can know what temperature of the ocean that they grew in because of the types of fat that are left in their lipids of their cell walls. Also, tree rings are sensitive to temperature. So over the last 30 years since the paleoclimatology started in the 60s, people were starting to amalgamate all this information. Warmest year, or the warmest decade of the last 1,000 years, also in 1998. Or the warmest century, at least, sorry. And that's what the El Nino looks like. Everybody kind of saw this before. El Nino is very big. That's why 2016 was so exceptionally warm around the world. And it's a process that we know a lot about now, and we can actually predict what the global warming spike is going to be for El Ninos because we know so much about it. There's still a lot we don't know about it, but we know enough about it to incorporate it into a large ensemble of climate models. Okay, 2000. You can see right now that's where 1998 was, and 1999 and 2000 were very cool relative to 1998. That actually happens after an El Nino, excuse me. But anyway, people The IPCC wasn't deterred about this big turnaround in global warming, which you can look up on the internet. A bunch of people were like, oh, the global's cooling, it's the ice age again. But it wasn't. The IPCC actually came out and said, hey, I bet extreme weather is getting worse. I think we're really quite certain that as the Earth gets warmer, extreme heat and extreme rainfall gets worse. And that's really simple. So like as air warms up, it can hold more water. And then basically you can think about it like loading the dice. It's like cheating. Climate change is weather cheating. And that's exactly what it is. And I was still holding strong to the haircut. You couldn't deter me, I know. And I left my brother in there because it's just as bad, but not quite. But anyway, without spending too much time, this is all going on when I'm that age, though. Just keep that in mind. Like, you don't know what's happening around you for a very long time. But in any event, in 2003, I'm 15, and that summer, 30,000 people died in Europe from a heat wave that was the strongest one they had ever seen in over 500 years. So only 2 or 3 years after the IPCC said that, hey, we should be worried about extreme weather, one such thing struck. And follow-up studies of that heat wave have confirmed that global warming loaded the dice for that heat wave to be twice as bad. Now this detection and attribution stuff, which you learned about happening in 1995, has gotten really good. Baton Rouge, the floods that happened in August this last year, that was made 3 times more likely by climate change. We can start to pick out these large climate events now, and we can say, hey, that is global climate change happening. Now, an individual storm outside, that's still just weather. But when it's a 5,000-year flood or a 1,000-year flood that's happening every couple of years or decades, it's no longer just natural variability. But I didn't want to hear about that because I was playing in a pop-punk band called Edo 100 because number bands were really cool. And I was also wearing a puka shell necklace and a Dare t-shirt, and those are my bandmates Watson and Mikey. But that's what it looks like in a map when you look at what the heat anomaly was like in a lot of cities in France. It was actually really, really bad. Like I said, 30,000 people lost their lives in this heat wave. And in fact, extreme heat, which is becoming more common even here in Virginia, this is the work I do now, the extreme heat here has gotten worse. And people get sick when it gets hot. So just keep that in mind. This is something that we can actually prepare for now. 2007, what a fine year. I'm graduating high school, and the IPCC that was formed when I was born comes with the conclusion that, yes, global climate change is humans' fault now. Sure, it's happened in the past, it wasn't our fault. Now it's happening, it is our fault. It is, 2007 was when, the Al Gore movie came out that everybody hates. Now we're going to see part 2, 10 years later. But the story hasn't changed since then. And I didn't want to hear about that because I was playing my guitar with my friends. But also, I know I want to save this because I was elected by my school, by my friends, by everybody in my school to speak at my graduation. And what I want to tell you is that being a nerd, or what people like to call a nerd, I was totally that. And I love science, and in this speech, I talk about climate change. I talk about things that, looking back, it's because I had science teachers around me that were pushing me to study these things that I really wanted to know about. So, anyway, I graduate high school. I go to college, and then this is really important. So I know it's just a bunch of squiggly lines, but this is one of the figures from the IPCC report that came out in 2007, and basically was like the nail in the coffin. Now I want you to look at 2 things in particular. The red line, which is the highest line on that figure, and then this black line, okay? So the red line is when we only put greenhouse gases into climate models, when that's the only thing that happens to the Earth, we see too much warming. We overestimate, the climate science community is happy to admit that we overestimate the amount of warming that you get when you that we've seen when you put just greenhouse gases into a climate model. But then, when you put all of the other things that we've spent 40 years, 50 years studying to understand, volcanoes, El Nino, clouds, aerosols, all that stuff, that's when we get the black line, the right answer. It doesn't just have to be human activities that are working on climate. Actually, the whole system needs to be there in order for us to get the right answer. And that's something that's really complicated about science sometimes. is that uncomfortable results that are repeatedly confirmed by subsequent studies are worth attention. So if you see something in your studies in the future and it seems weird, follow it up. It might just change the world. So 2011, I'm 22, and the human population reaches 7 billion, and unlike what scientists have been saying for decades, heat-trapping gases are still increasing at an alarming rate. And I just so happened to win a research award as an undergraduate at Augustana College, and I was elected to speak at my college graduation. And in this same speech, I basically say the same stuff, that it's up to us, our generation is the one that needs to chase the solutions for this, because obviously no one else is picking up the slack. So, and I also quoted Hunter S. Thompson, which I all hope that you read sometime in your adulthood. But in any event, that's what human population had done since about 1800. It's hard to see the numbers, but there's one of those things that the Anthropocene is a very clear imprint of a huge upward trend, very fast. And 7 billion, we're expecting a couple more billion for dinner over the next couple decades. We need to figure out, like, what are those people going to eat? Where are they going to eat that stuff? And how are they going to power the stuff to cook that food? And what, those are questions that we need to be asking right now. Anyway, 2016, I finished my PhD at Oregon State University, which was awesome. And I also start working at the Science Museum of Virginia here in Richmond. I was basically able to get a really cool job. I'm happy to be here. And but there was also this paper by Richard Seavey, who's at the University of Hawaii. And he was able to using paleoclimatology, to show that the most recent time where Earth's climate was so warm that a lot of stuff died out, called the Paleocene-Eocene thermal maximum, that we are emitting heat-trapping gases 10 times faster than what they did to reach that kind of heat amount on the planet. So we are far outpacing the natural world in any time for the last 66 million years, since the end of the dinosaurs. So, but that's me at the Science March in DC just a couple of weeks ago. And my sign says isotopes are isodope, okay? It was really funny because, and I know that's not 2016, that's 2017, you can, whatever, plus or minus 1 year. And the funny thing that I had was an old guy who had worked at the Department of Energy for the federal government for a number of years came up to me, and it was like this generational exchange. He says, "Why are isotopes dope?" And I was like, kind of hard to explain. But I realized he thought I was saying that they're dopey, because he's an old guy, and dopey was a bad thing in the 60s or 50s or whenever he was, I don't know how old he was. But I said, no, dope is like slang for rad. And then he goes, okay. But then he said, we're learning. And I was like, yes, we are. That's very nice. So anyway, I now spend a lot of my time learning how to communicate with people about science, get them excited about it, and trying to get them to enrich their lives through the process of science. But this is kind of the last, we're nearing the end, I know. It's hot in here too, but this is kind of, we're looking at the amount of temperature change and the duration of time. And then this blue line is the amount of heat-trapping gases put into the atmosphere by the Earth over many thousands of years. So it's this long gradual hump, right? Well, the red line is what we are doing. We're putting 30 billion metric tons of carbon dioxide into the atmosphere every single year. Every single year. We've so far outpaced the world. This is the Anthropocene. We're here, we're living in it. And that's kind of the difference. So we're hoping for the best. And what's really amazing is, like, even if tomorrow we were to shut everything off, every last toaster and car and power window and anything that creates heat-trapping gases, climate change doesn't stop. It doesn't stop for millennia. So that's where we're at right now. So 2017 is the gold star. That's what's predicted by NASA right now to be the temperature anomaly, and that's about 1 degree Celsius. So there we are. That's how far away we are from home. You just went through the entire 140 years of data, learned a little bit about me, and the thing that I want to say is that this situation, the Anthropocene, doesn't suck for our parents. It sucks for us. It's really something that our kids, should we choose to have them, are going to have to deal with. And that's something that I know is uncomfortable to hear. It's not a very pleasing thing, but we need to figure out, like, our generation can figure this out. And to prepare, mitigate, and adapt. We know the kinds of things that will happen. Heat waves, extreme weather. We can become resilient to those things. We can build better cities. We can make people in countries that don't have electricity have smart grids that don't crash. We can update our existing infrastructure. It's all there for us to do. It's just whether or not we're going to choose science to get us there. Okay? So that unfortunately requires bipartisan stuff, which right now isn't working right. All right? We all know that. It's just not working very well right now. It's not broken, but it's bending. So hopefully we can help that process getting back together. We're a very social generation. But it's a huge opportunity for you. It is. I know it's bad. I know I just made everybody sad, but it's a great thing. It's a great thing for everyone in this room. There is so much science to be done in health. Who here is interested in going into the health sector? Yes. Okay, tropical diseases, heat-related illnesses, allergies. How are we going to make people healthier for longer parts of their lives? Using food and, all of that stuff. That's a question that's out there. That's attainable. Then, energy. Who wants to go into renewable energy or some other form of energy? Yes. Yes. Thankfully, here in this state, we have a governor that's been very supportive of renewable energies. And so that can be your route. You can figure out how to make that battery that lasts forever. It would be fantastic. Then the resilience and adaptation. But the biggest thing I want to talk about is environmental equity. The thing that we can figure out to make it better for everybody, and not just the people that, because like I said, there are going to be a couple more billion people coming to dinner. And we need to figure out how that, given climate change, because it's going to happen, it's going to continue happening, how do we move forward from here? And science can lead us down that way, that path, and all of you are part of that team now. And it's really awesome to have the opportunity to talk with you about it. And these are all things that you seriously, I know old people like to say, you can do this, you can make it better. You really can, because I've experienced that in my life. I was very fortunate to be able to make something a little bit better. And ultimately, don't let the haters get you down, because people will try and hold you back. No doubt they will. And don't let them do it. Don't let them do it. I'm Johnny Hoffman. Thank you so much. You're all amazing. Enjoy the rest of the meeting. Thank you so much. That's the coolest thing ever. Sit down before you fall down. It's hot in here. We have time for questions? That's awesome. Okay, we've got another microphone down here. I guess they'll kind of run around and try and find you if you have a question. So, you've got plenty of time. Don't be shy. All right, we got a question over here. Maybe this person has the same question you do, and it would be cool to be like, hey, I know that. That's cool.
Well, thank you for coming. I look forward to voting for you in the next presidential election. My first question is, okay, so we're at a position in our lives right now where we can go towards the direction, like you're saying, to make things better. What do you suggest for us as students entering college or high school into pursuing that future and making it a reality? What are some steps that are practical, etc.?
Yeah, so that's a great question. And so the first step, you've already taken it. So recognize that the step that you've done to make a research project has already sent you on a pathway for making this reality. If you really want this, you've already done a lot of the work early on, okay? Second thing, in college, there are going to be people that are like, oh, biology is really hard, or physics is really hard, or math is really hard, or computer science is really hard. And it is. Geology, not so much that hard, but you could try that if you want to. But the biggest thing that, I mentor undergrads now, and so the biggest thing for me is that you ask for the opportunity to contribute to the science that somebody's doing at your university. One big thing to do is if you want to go to college, if you have the ability to go to college, you're fortunate enough that you have the ability to go to college, seek out the college that does stuff that you think is cool. So VCU is a great example of a university that offers seriously everything. Oregon State, my alma mater, great place to go. Just go to your passion. You know something, maybe you know that what you did for this high school thing, the VJAS meeting, you don't want to do that anymore. I did that same thing in college. I'll give you a short story. So I did a mineral efficacy experiment, and everybody in the room just fell asleep. So I was asked by a company to measure how sturdy their sandblasting sand was. Yeah, what? I know, and I did it. And I was like, and they were like, you want to be an economic geologist? And I was like, I assuredly don't anymore. So I did something that was like not too, don't be afraid to do something that you don't like, but so really figure it out. College is really great for a lot of things, but just be engaged with the professors that you think are doing cool work. Be annoying. I was super annoying. I learned how to write emails day one. So write emails, go somewhere that you want to go, and again, don't let the haters get you down, and do something hard, because it's more fun to get to the end of the hard thing than it is to do the easy thing and be like, what am I doing now? So thank you for your question.
Can you touch on GMOs versus organic food supply for the 2 billion that are going to reach the 9 billion in 2050?
So I'll preface this with, there are probably some people in this room, adults and young people alike, that we like certain scientific information that makes us feel good. When it confirms something that we view about the world, it's really comforting. When instead you are presented with a scientific argument and a mountain of evidence that is against something that you hold close to your identity or your worldview, it's really hard to accept that. So I'm going to preface what I'm about to say with that statement. And that GMOs, there was a big research, a National Research Council review of 30 years of GMO food data and growing data, environmental data. GMOs are not unsafe. They are actually better for biodiversity, and they increase crop yields in small farms. So, but what I ask for is, before you put up the pitchforks, if you're like, no, GMOs are bad, is that sometimes we conflate scientific issues into one. So a GMO, you might think industrial ag, you might think Monsanto, you might think these things, hormones and those things. You need to look at the scientific issue for the individual variables, like we've done with climate change. You need to sub out those variables. GMOs are not unsafe. We do it every day. So I think one thing that the GMO argument brings is the opportunity to feed more people using more conventional organic practices. An organic farm can benefit from using GMOs. So that's what I would say about that. Thank you for that question. There's a couple people over here that have held their. Well, we can take this one, but then I'll maybe go over to this side for a question.
So global warming has become a big issue, and a lot of people are aware of this now. Have you noticed that more people are taking care of the earth, or have you seen it gotten worse?
Can you say that one more time?
Global warming has become a bigger issue, and a lot of more people are aware of it. Have you noticed that the earth people have taken better care of the earth, or has it gone down?
So that's a fascinating question, and what's really cool, so are there people that are interested in social science here? Yes, the way people learn and think. That is revolutionizing the way that we think about climate change. And I'll tell you why. The question about global climate, 70% of Americans acknowledge that global climate is changing. 25 or 30% think that it's actually affecting them. So do you see that disparity? Until global climate change is at your door, you don't do anything about it. So what we're doing at the Science Museum of Virginia, to plug where I am at now, We are making climate change, trying to make it relevant to people in Virginia. You can go to our YouTube page. You can follow me on Twitter. You can follow us on Facebook, Science Museum of Virginia. We're trying to make that jump. Because you're right. Actually, no one's doing anything. No one's really changing yet. And until people are confronted with it in their everyday lives, they're probably not going to do anything about it. So it's a fascinating question, and thank you for asking it. Thank you all for being patient. Hopefully we can get to all of you. Were there people in the back too that had questions? We'll try and, okay, we'll send them back. Go ahead.
So this goes like back to the beginning of your talk, but like you said that you found like your own professor found a fossil in Antarctica. Like, how could there be a fossil of a big dinosaur?
That's this wonderful thing that took a really long time for people to accept. So remember how I said that scientific data and evidence that doesn't fit with the worldview is really uncomfortable? Well, there were hundreds of years where people thought that the continents didn't move around at all. In fact, everything had just always been where it was. Africa had been there, America had been there, Europe had been there, Antarctica had always been there. But actually, Antarctica used to be part of the rest of the world and has slowly moved to its present position. So when dinosaurs were around, they were able to live in Antarctica because it was further towards the tropics, towards the equator. And then slowly over time, it has become the ice house that it is now. That happened sometime in the early part of the Paleocene is when that separation really happened and the ice sheet grew really big. So the Jurassic was about 150 million years ago, and ice sheets didn't form there until about 55 million years ago. So it's a long time period that that continent was moving very slowly southwards, okay? Does that make sense?
It just wasn't frozen then?
One more time?
Antarctica just wasn't frozen then?
Right. Because it was closer to all the rest of it was closer to the equator and slowly moved that way. It's really fascinating. Okay, cool, yeah, so slowly move, a little bit further back, because people have been asking.
Hello. So,
Hello.
Our statistics teacher always tells us to caution us when looking at statistical data. So one of his favorite sayings is that correlation does not imply causation. So how do you know that's the CO2 causing the climate change and not an intervening variable that you haven't found yet?
Right, that's such a sharp, The thing is if that thing is waiting out there for us, that will win every single World Science Prize ever. But our fundamental understanding of physics is what underpins the heat trapping gas effect. So to say that there's something else, to make it more complicated, and to say that there's something else that's rising just as fast as global temperature and CO2, and causing everything else around the world, like ice to melt, glaciers to recede, all of those things happening point to something that globally makes the world warmer. The only thing that we know for a fact that does that is CO2 and other greenhouse gases. So while we might not know of this wonderful, fanciful thing that is causing it, I implore you to search that thing out for the rest of your life.
Nice answer, sir. Thank you.
Yeah. Thanks for that question, by the way. Statistics. Actually, a side story, one of my favorite things about statistics is the number of Nicolas Cage movies and the number of people that die by drowning are correlated. I don't know. Just saying.
We talked about that. So, would you say that it's more important to work on prevention or adaptation?
Can you say that one more time?
Would you say that it's more important to work on prevention or adaptation?
Well, certainly the sooner that we can turn it all off, all the hoses of CO2 going in the atmosphere, the better. Okay, so don't get me wrong. I'm not saying that at all that we should not aim to reduce the amount of heat-trapping gases that we put into the atmosphere. But the climate has already changed. A lot of our infrastructure has not caught up to the new threats that we face every single year. So I actually advocate for a holistic approach to that. Resilience, adaptation, and mitigation through greenhouse gas reductions. So I think of it as we need to be pushing full gear for all of those things. So yeah, pick which door you want to go through and chase it, all right? Thank you for the question. Work your way back up here. Well, I think we'll get to you. Thank you for all of these questions. Keep them coming. I mean, if you're not bored yet, I guess.
First, thank you very much for the enlightening talk. I was actually wondering what we can do as students and as we're rising to adulthood to raise awareness and to help prevent and adapt to climate change as a whole.
Okay, that's such a fascinating and wonderful question because as you approach, so when you get to college, actually right now, what grade are you in?
7th.
You're in 7th grade. Fantastic. Okay, one of the major sources of greenhouse gases to the atmosphere is actually food waste. If all of the food that we wasted all around the world acted as a country, it would be the 3rd largest emitter of greenhouse gases in the world, behind the US and China, okay? Food waste by itself. So one thing that we can think about, one thing that we can all think about is do we overbuy how much food we eat? Do we eat too much? Do we throw away too much food? And when we throw it away, are we putting it in places like a dump where it can't be used for a beneficial purpose? So one thing that I would recommend, when you go back to your school, see if there are other people and teachers that are interested in starting some sort of composting program. Finding places, one of the big things about food also is that it travels a long distance to get to where you're going to eat. So an average American meal travels 1,500 miles to get to your plate. 1,500 miles. So if you can figure out how your school, if you and a couple of your friends can figure out how your school can reduce food mileage and food wastage, you're doing a great first step, okay? Other things, support the renewable energy project that your crazy physics teacher wants to put on the roof. Think about ways in your hometown that people have done that together. And it's always better to move together and have a group around you than try and act by yourself. So find some people that are like-minded, make a plan, and talk to somebody who will listen to you. And then as you get older, those sorts of behaviors and community engagement is only going to benefit you as you get older, okay, bud?
Okay, thank you. I'll try to implement everything you said.
All right. Yeah, I hope you wrote it all down.
Thank you so much.
Food waste. Food waste. Food waste.
So this is gonna sound kind of vague, but I'm really interested in chemistry, and in chemistry, a chemical reaction can't be undone. So is there a way that we could possibly reverse some of the effects of these variables that we have already put into play, or are they permanent? Will they stay here forever?
So what's interesting is that I can certainly dissolve salt into water and then evaporate that water out and I get salt back. So there are ways to make reactions go forward and backwards. So what's really amazing is that there have been proven ways that we can take CO2 out of the atmosphere and inject them into rocks. So look it up when you get home, injecting CO2 into basalt. Basalt rocks and CO2, it'll be one of the first things that you see pop up on Google. That's one way that we think that we might be able to do that.
That's really cool, thank you.
It is cool, yeah.
What was the name of your band? Did you guys sing about science?
No, we didn't sing about science. But I would do a shameless plug. If you go to YouTube and you type in "the sound of skeptics," you might find a video of me singing about science. So it's called "The Sound of Skeptics." It's some people will recognize Simon and Garfunkel in this room, mostly the teachers. But oh, then you would love that. You would love that song. So yeah, we didn't sing about science back then, but I do that now.
We'll take one more question.
Oh, did you find it? Yeah. It's real. Try and get to everybody. Try and get to everybody.
All right, so you said that your project was basically based on a few hundred years of data supporting global climate change in a positive direction.
What? Let's start over.
So you said your project was based on a few hundred years of data on the Earth's global temperature increasing, correct?
So what I showed you in that 140 years of data is not at all my work.
Yeah.
That's the work of countless...
It's the averages of the temperature.
What's that?
The Earth. It's the Earth's average temperature.
You're right. Yeah, well, an anomaly from the Earth's average temperature.
So are you assuming Earth's average temperature over 140 years on an Earth that's millions of years old?
So there's a couple ways that we can go about this. So I'm a paleoclimatologist, okay? So I study hundreds of thousands of years of Earth climate data. And if you want to not look up my YouTube picture or YouTube videos, go and actually look up a paper from my PhD that was published in the journal Science back in January. And using data from 130,000 years ago, my colleagues and I were able to show that we are outpacing, yet again, in another way, the Earth's natural ability to warm itself. So we try not to make any assumptions, actually. And the cool thing about paleoclimate is it shows just how unique the last 140 years have been. So does that help clarify it?
Yeah, I'm not trying to say I'm part of that 30% that doesn't believe in climate change. I'm just kind of skeptical as in that the Earth is millions of years old and that we're only using 140 years of data to say that the Earth's climate temperatures are increasing.
Right, and you'd be right if we were only using 140 years of data. That would be probably too short. But we have millions of years of data, and we are quickly, very rapidly, going outside of what the Earth was able to do by itself for all those millions of years. So again, I will stress again that it's the uniqueness of the last 100, 200 years that is really what we're comparing to for the millions of years. So you're right, the Earth has been around for a very long time, and that's why we know how special what's happening right now is.
So you're saying humans directly are causing the Earth to increase the global temperature?
Yes. Yes. We got there. Thank you for the question. Excellent question.